Hello everyone, welcome to the lecture again. In the last class, we learned about how to find out the moment of inertia about an axis which has a direction cosine L, M and N. We learned about the inertia matrix and the principal moment of inertia and how to find out the direction cosine of the principal axis of inertia. Let me first summarize these results and then we will look at couple of examples. So, the moment of inertia about an axis that has direction cosines, let us say L, M and N. Okay. So, remember I have a rigid body and let us say a point O is given and this is x axis, y axis and z axis, and then I want to find out the moment of inertia of this rigid body about an axis OL whose direction cosines are L, M and N. Then the moment of inertia I about line OL will be Ixx L square plus Iyy M square plus Izz N square minus 2I xy Lm minus 2I yz Mn minus 2I zx Ln. Let us call this equation number A. Then the inertia matrix I was Ixx, Iyy, Izz and then we have minus Ixy minus Ixz minus Ixy minus Iyz minus Ixz and minus Zy. Okay. Then the principal moment of inertia can be found out by using the following equation: Ixx minus I minus Ixy minus Ixz minus Iyx Iyy minus Iyz minus Izx minus Izy Izz minus I and put this determinant equal to 0. Now, this equation will give you 3 solutions for the I. So, let us call them I1, I2 and I3, call this equation number B. So, now we have the principal moment of inertia, then the direction cosine L, M and N of a principal inertia axis for let us say each I is okay. So, that will be Ixx minus II. So, let us say I choose the first I. So, that is I1 into L minus Ixy M minus Ixz into N, that is equal to 0. And I have minus Ixyl plus Iyy minus I into M minus Iyz N equal to 0, and then we have minus Izx into L minus Izy into L plus Izz minus II into N equal to 0, along with that L square plus M square plus N square equal to 1. So, let us call this equation number 3, and the solution of this equation will give you the L, M and N corresponding to first I1. If you use I2, then the L, M, N corresponding to I2, and similarly for the I3. So, that will be the direction cosine of the principal inertia axis. Now, let us look at one problem statement, and the problem statement is following. Question number 1, the assembly consists of 3 small balls, each of mass m, that are attached to slender rod of negligible mass calculate the moment of inertia of the assembly about the axis OA. Okay. So, we have this slender rods, and let us say it is given that this one is the x axis, this is the y axis, and we have the z axis, and we have this slender rod, and from here I have two masses. So, this rod is parallel to the x axis, then we have this axis which is parallel to the y axis, and then we have this slender rod which is parallel to the x axis, and this is, so all of them has mass m, and let us say this one is 1, it is given there, this one is 2, and this is mass number 3. Okay. The length is also given. So, this is B, this is B, this is B, this is B, and this is also B. Then we have the x is OA, about which we have to find out the moment of inertia. Let us say the unit vector along OA is lambda or lambda cap, and it is given that this angle is 60 degree and this angle is 40 degree. Okay. Now, first let me write down the coordinate of mass 1, 2 and 3. Note that this is a 3 dimensional problem. So, here the coordinate of mass 1 will be B, 0 and minus B, okay, because you have to move B towards the x axis, about the y axis you do not need to move. So, therefore, this is 0 and then minus B along the z direction to reach at the mass 1. Similarly, for mass 2 the coordinates are 0, B and B, and for the third mass the coordinate is minus B, 0 and B. So, let us first find out the moment of inertia and the product of inertia for ball 1. Okay. So, for ball 1 the moment of inertia about the x axis, which is equal to m r square. So, here r will be m y square plus z square. Now, we have to put the value of y and z for mass 1 from here. So, let us put that, it will be m, y is 0 plus z is minus b square, and that will give you m b square. This is the moment of inertia of mass 1 about the x axis. Now, let us look at IYY, moment of inertia about the y axis, it will be m z square plus x square equal to m, z is minus b. So, therefore, minus b square plus b square, and that is equal to 2m b square. Similarly, I z z. So, that is equal to again m x square plus y square, that will be equal to m b square. Now, the product of inertia I x y. So, I x y, note that here y is equal to 0, because the definition is m into x into y, but since y is equal to 0, therefore, the product of inertia will be 0. I y z, again it will be m y z, but then y is equal to 0, therefore, it will be 0. Now, let us calculate I z x, that is equal to I z into x. So, this will be equal to z is equal to minus b and x is equal to b. So, therefore, it will be minus m b square. Okay. So, we have the moment of inertia and the product of inertia for ball 1. Now, let us look at ball 2. For ball 2, the moment of inertia about the x axis, similarly I am not writing down the formula, it will be 2m b square, I y y will be m b square, I z z is equal to m b square. You can check it by putting the coordinates, and the formula is already given here. Okay. Similarly, I x y will be 0, I y z will be m b square, and I z x will be 0. Now, let us look at ball 3. Okay. So, here I x x will be m b square, I y y will be 2 m b square, I z z is equal to m b square, and I x y will be 0. Why? Because for ball 3 we are here, I x y will be equal to m x into y, but then y is equal to 0. So, therefore, it will be 0, I y z will also be 0, and I z x will be minus m b square. Note that while calculating this, we have used the fact that the ball is small. Okay. So, it is not a sphere, it is a point mass, therefore, the moment of inertia was m into r square and so on. Now, the total moment of inertia and the product of inertia will be the sum of ball 1, 2 and 3. So, total moment of inertia and product of inertia will be, so for example, I x x will be the sum of this plus this plus that. Okay. So, we have 1 plus 2 plus 1 equal to 4 m b square. Let me write it down on the next page. So, I x x will be 4 m b square. Similarly, I y y will be 2 m b square plus m b square plus 2 m b square. So, that is equal to 5 m b square. I y y equal to 5 m b square. This is the moment of inertia and product of inertia of the assembly, okay, of the entire structure that we have. Similarly, I z z, you can sum them up, it will be 3 m b square, I x y is equal to 0, I y z equal to m b square, and I z x equal to minus 2 m b square. Now, in the question statement, we have been asked to calculate the moment of inertia of the assembly about OA. So, what we have to do is, we have to put this value in equation number A, but for that I should know what is the L, M and N, that is the direction cosine of the axis OL. Okay. So, for that let us look at the unit vector along OA. So, the unit vector, let us call it lambda cap. So, lambda cap will be, so let us look at the projection along the x axis. So, it will be cos 40 degree, cos 60 degree into I cap plus cos 40 degree into minus sin 60 degree j cap plus sin 40 degree k cap. So, this is the unit vector which I have wrote in terms of I, j and k. Okay. This can be find out because the value of cos 40 and cos 60 we know. So, it will be 0.3830 I minus 0.6634, let me put a 0 here, j plus 0.6428 k. Okay. So, this is your L, that is your M, and this is your N. Okay. The direction cosine, the value of cos alpha, cos beta and cos gamma, where alpha, beta, gamma is the angle that it makes from the x, y and z axis. So, let us put this in equation number A. Remember, the equation number A was this. So, IOL, or here IOA will be equal to I x x L square plus I y y m square plus I z z n square minus 2 I x y L m minus 2 I y z m n minus 2 I z x L n. Okay, this was our equation number A. So, we have I O A equal to, now the value of I x x is 4 m b square. Let me take m b square outside. So, we have 4 into L square is 0.3830 square plus I y y is 5 m b square. M b square I have taken as a common factor. So, that is 5 into m square is minus 0.6634 square plus 3 into 0.6428 square minus 2 I x y. So, that is equal to 0, and then minus 2 I y z. So, 2 into I y z is just m b square, I have taken outside. So, 1 into m into n. So, m is 0.6634 into n is 0.6428 minus 2 into I z x is minus 2 m b square. So, minus 2 and L and n. So, the value of L is 0.3830 into n is 0.6428. Okay. And this can be calculated. So, that comes out to be 5.86 m b square. This is the moment of inertia of this assembly about the axis OA. So, this is how we can find out the moment of inertia about any axis if we know the direction cosines. Now, let us look at another problem statement. The assembly in the figure consists of two identical thin plates, each of mass m and thickness t. For point O, determine number 1 the inertia tensor, with respect to the axis shown, and the principal moment of inertia. Here this assembly is consists of two plate. To find out the inertia tensor of the assembly, we have to find out the moment of inertia and the product of inertia of both the plate. So, let us first look at the plate 1. So, plate 1 is like this, we have the y axis, we have the x axis and we have the z axis. Then plate 1 is like that, and it is given that this length is a, this is also a, that is also a. So, this is our plate 1, and the second plate is like this. Okay. So, this is also a and this is also a, that is also a. Okay. Now, let us find out the moment of inertia and product of inertia for plate 1. Okay. It is given that the thickness of the plate is very small. So, I x x, the moment of inertia of this plate about the x axis. Okay. So, which is this axis. Okay. So, the moment of inertia of the plate of length L, we already know it is m L square divided by 12. So, here it will be m into length is 2a square divided by 12 and that is equal to m a square divided by 3. The moment of inertia of the first plate about the y axis, which is this, that will be equal to the moment of inertia, let us say about this axis plus m into h square. So, I am just using the parallel axis theorem. So, that will be equal to m a square divided by 12. This is the moment of inertia of plate 1 about the axis which I have drawn by the green dashed line, plus m into h square. H is a by 2 because we want to calculate about the y axis. So, this is a by 2. So, therefore, m a by 2 whole square and that is equal to m a square divided by 12 plus m a square divided by 4 and that is equal to m a square divided by 3. Now, note that this plate is in the xy plane, therefore, we can use the perpendicular axis to find out the moment of inertia about the z axis and I z z will be equal to I x x plus I y y. So, herein I am using the perpendicular axis theorem because the plate is in xy plane and herein I have used the parallel axis theorem. Okay. So, this is equal to m a square divided by 3 plus m a square divided by 3 and that is equal to 2 m a square divided by 3. Now, let us look at the product of inertia. So, note that this thickness of the plate is very small, it is given that it is small, this is a thin plate. So, therefore, in the z direction it will be 0 because the thickness is small. So, I have thickness z is equal to 0, therefore, I y z is m into y into z, but then z is equal to 0, therefore, this will be equal to 0 and also I z x will be 0 because again z is equal to 0. Now, what is left is I x y. Now, I x y will also be 0 because the x axis here is the symmetric axis for this plate. Okay. So, I x y will also be equal to 0, since x axis is the axis of symmetry for plate 1. Okay, so, either you calculate or from the symmetry you can say, because the limit has to be from minus a to plus a, and therefore, it will be 0. Now, let us consider plate 2. So, for plate 2 also we have to find out what is its moment of inertia about the x axis, y axis and the z axis. Note that this plate 2, it lies in the y z plane. Therefore, moment of inertia about the x axis I can find out using the perpendicular axis theorem, and for that I should know what is I y y and I z z. So, let us first calculate what is I y y. So, that is the moment of inertia about the y axis, and for this I can use the parallel axis theorem. So, the moment of inertia of this plate about this green axis which is passing through the center will be m into L square divided by 12, L is here 2a. So, this divided by 12 plus from the parallel axis theorem it will be m a square. So, here I have used the parallel axis theorem, okay, and this comes out to be 4 by 3 m a square. Now, the moment of inertia about the z axis, again I can find out if I calculate the moment of inertia about this blue axis and then use the parallel axis theorem. So, here it will be m a square divided by 12 plus m into a by 2 square, because this is a by 2. Okay. So, that comes out to be 1 by 3 m a square. This is again the parallel axis theorem, and I x x will be I y y plus I z z, because the plate lies in the y z plane. So, that is equal to 4 by 3 m a square plus 1 by 3 m a square, and that is equal to 5 by 3 m a square. Now, this plate again has a thickness almost 0, because it is very thin. So, therefore, I can say that x is equal to 0, because thickness is small. So, therefore, x is equal to 0. Therefore, I x y, which is m x y, but x is equal to 0. So, therefore, it will be 0, and also I z x. Okay. Now, let us calculate I y z, and for that I can use the parallel axis theorem. So, I y z will be equal to, let us say this axis is y prime and this axis is z prime. So, that will be equal to I y prime z prime plus, from the parallel axis theorem I can say m into a into a by 2, because this is a and this is a by 2. Okay. Now, I y prime z prime will be equal to 0, because the plate is symmetric about the y prime and z prime axis. So, that is equal to 0 plus m a square divided by 2, which is equal to m a square divided by 2. So, now we have the moment of inertia and the product of inertia of plate 1 and plate 2. Now, the total moment of inertia and the product of inertia will be, so let me write down, total moment of inertia and product of inertia will be I x x equal to, I x x will be equal to this plus that. Similarly, I y y will be equal to this plus that, and I z z will be equal to this plus this. Okay. So, let me write it down. It will be equal to m a square divided by 3 plus 5 m a square divided by 3, that is equal to 2 m a square. I y y, similarly it will be 5 by 3 m a square, and I z z will be equal to m a square. Now, let us look at Ixy, Ixy was 0 and here Ixy was also 0. So, therefore, Ixy will be equal to 0 plus 0 equal to 0, Iyz will be equal to Iyz. So, here it was 0 and here Iyz was ma square divided by 2. So, that is ma square divided by 2 and Izx was 0. Therefore, the inertia matrix I will be equal to Ixx, so which is 2 ma square 5 by 3 m a square and Izz is m a square, and then we have 0 0 0 minus half m a square 0 and minus half m a square. Okay. Now, let us look at the second part. In part B, we have been asked to find out the principal moment of inertia. So, that will be the solution of the following determinant: 2 m a square minus I 0 and 0, 0 5 by 3 m a square minus I and minus half m a square, 0 minus half m a square and m a square minus I equal to 0. So, let us solve this equation. So, we have 2 m a square minus I into 5 by 3 m a square minus I into m a square minus I minus 1 by 4 m square a to the power 4 is equal to 0. So, this I can rewrite as 2 m a square minus I into I square minus 8 by 3 m a square I plus 17 divided by 12 m square a to the power 4 is equal to 0, and this equation gives you the 3 values of the I. So, here I1 will be 2 m a square, I2 will be equal to 1.9343 m a square and I3 will be equal to 0.7324 m a square. Okay. These are your principal moment of inertia. With this, let me stop here. See you in the next class. Thank you.